Hello, today we talk about the time-independent perturbation theory. Let's say we have an equation, an eigenvalue equation which we can't solve for the Hamiltonian 8. Now En will be the eigenvalue associated with the eigenstate, and now we can't solve this equation. Let's say that we can nevertheless expand H as H0 plus a small perturbation term. Now this term is small because lambda is small, so let's say we can expand H like this, and let's say that we know how to solve the eigenvalue equation with H0. So we write H0 and 0. These are the eigenvectors of the unperturbed Hamiltonian. This will be En0 and 0. So let's say we can solve this equation. We can't solve this equation, and we can expand H like this. Now we do another hypothesis, which is that we can write En, the eigenvalues associated with the eigenstate N, as En0, the unperturbed eigenvalue, plus other perturbation terms. This will be the first order perturbation term, En1 plus lambda squared En2, and so on. So in this notation, the number up is the order of the term. So this is the 0 order term, the first order term, the second order term, and this is a very useful notation. The same is for this, the unperturbed order 0 term, and this is the first order term. And we do the same, we suppose that we can do the same with N0, with N, so we write N as a perturbation of N0. So N0 plus lambda, first order term, N1 plus lambda squared, second order term, N2, and so on. So we can't solve this, we can solve this, and we can write this like this. And let's see if writing En and N like this, we can find an approximate solution to this equation. Now we also do other three assumptions. One is that N and M, all these eigenstates will be orthogonal. So the bracket product and M will be delta and M, and we assume also completeness. So the sum of the ket bra product and N over all the N is the identity. And then we also assume that we have no degeneracy, so that two different eigenstates will correspond necessarily to different eigenvalues. So we start by expanding the terms in the equation we can't solve, which was H minus En times N equals 0. I have brought everything to the left. We expand the terms, we expand H is H0 plus lambda H1, and then we have to expand En is En0 minus lambda En1, and so on, and it is multiplied by the eigenstate, and which we also expand, N0 plus lambda and 1, and so on. So remember that H has only two terms, the order 0 term and the order 1 term, and instead En and M have infinite perturbation terms. So we now isolate terms with the same lambda for simplicity, and so here we write H0 minus en0 lambda, sorry, without lambda, this is with our order 0 terms, plus h1 minus en1 lambda, and then we only have terms with en, so we have minus en2 lambda squared minus en3 lambda to the cube, and so on. So now we must have the order 0 terms equal to 0, the order 1 terms equal to 0, and so on. So this is a multiplication of these expansions. So for the order 0 term, we only have to multiply the 0 term here by the 0 terms here, and we have, which are these two terms. So we have h0 minus en0 n0 equals 0, and we already knew this because this is the unperturbed eigenvalue equation. Instead, for the order 1, we have to take the 0 term here and the 1 term here, and then we have to sum the 1 term here times the 0 term here, because they must have order 1, so the order in the multiplication must add up to 1. So 0 term is h0 minus en0, order 1 is n1, and plus order 1 here now and order 0 here now, h1 minus en1 times n0, this equal to 0. For the second order we do the same. We will take the order 0 and then the order 2, then the order 1 times the order 1, and then the order 2 times the order 0. So we will have h0 minus en0 times n2 plus h1 minus en1 times n1 minus en2. Remember that h only has the order 0 and the order 1 term, so now we only have en term, so minus en2 and 0 equals 0. And you see that in general for the order k, we will have to sum the 0 terms, to multiply the 0 terms by the k terms in the eigenstate, then we multiply the order 1 terms in the Hamiltonian and the k minus 1 terms in the eigenstates, then the second order term times the k minus 2 terms, and so on up to the order k terms in the Hamiltonian and the 0 order term in the eigenstate. So we will get something like these first two terms we have the Hamiltonian, the other we have only un, and so we write first the first two terms, which are h0 minus en0 times nk plus h1 minus en1 times nk minus 1, and then we have only terms without the Hamiltonian, so which are minus en2 nk minus 2 plus minus order 3 term here and order k minus 3 term here, and so on up to the order k in the Hamiltonian and order 0 in the eigenstate. So we have an equation like this equal to 0, an equation like this for each order k. Now I have written here these equations, and I want to show now an important property to the corrections to this eigenstate, and which will be very useful in a few moments. This property is that we can always choose these corrections n0, n1, n2, and so on to be orthonormal. There is a very simple orthonormalization algorithm which goes like this. Let's suppose n0 solves this equation. Let's suppose n1 solves this equation, but n1 is not orthonormal, is not orthogonal to n0. So n1 we have a component along n0. The component will be, let's say, c times n0. We can remove this component, and if we remove this component, we will get minus c times h0 minus e n0 n0, right? Because it was a component of n1 and we have removed it, so we have this time multiplying it, and this one is 0 because of the first equation. So we can remove this equation, we can remove this component c and 0, and get a vector, an eigenvector n1 orthogonal to n0, which is also a solution to this equation, and also a valid first order term. And we have k minus 1, the first n1, n2, and nk minus 1 orthogonal. Then we can do the same and remove components from nk to make them all orthonormal. So we can always choose n0, n1, n2 to be orthogonal, and from this moment we will assume that they are. So now let's simplify these equations. For degree 1 we have h0 minus en0 times n1 plus h1 minus en1 n0 equals 0. Now a trick to solve these equations is to multiply the left hand side, both sides by n0. So we do the bracket with n0 here, and so we have here n0 times this plus n0 times this. So now this becomes n0 times h0 minus en0. This was the equation for the unperturbed Hamiltonian, and it was equal to 0. So all this term is equal to 0, and we are left only with this term, and we have n0 h1 n0 minus n0 en1 n0, and we can take en1 out, and since these eigenstates are orthonormal, this is 1, so we get that the first perturbation term in the eigenvalue is n0 h1 n0. So we got the formula to evaluate the first order perturbation term. Now what about the other orders? They can also be simplified. In fact, to the left we always multiply by n0, and here we will have, instead of n1, we will have k, and here we will have k minus 1, and then we will have terms with only the energy, so minus n0 e n2 n k to the minus 2 minus n0 e n3 and k to the minus 3 and so on up to minus n0 e n k n0 equals 0. So this term is always 0 because we always have n0 times h0 minus e n0. Here instead we have n0 h1 n k minus 1 minus, we can take this out and we get en1 times n0 and k minus 1, and then we only have terms with en, and so we get minus en2 n0 and k to the minus 2 and so on up to minus n0, and we already take out e and k times n0 and 0. Now all these eigenstates n are orthonormal, so we will have that these products n0 and k to the minus 2 n0 and k to the minus 1 are all 0 except for n0 and 0, which is 1 by orthonormality, and so we get n0 h1 and k to the minus 1 minus en k equals 0, and we write it better like this, equals e n k. So we can get very simply the formula for the term of degree k, the correction term of degree k, which is n0 h1 and k to the minus 1. So to know the correction of degree k, you only have to know the correction in the eigenvalue of degree k minus 1, because the correction of degree k was cancelled out here, and all the other corrections, all the other degrees were cancelled out by orthonormality. So we found this form for the first order correction to the energy, and this can be written in a more compact form as h1nn when we have introduced the matrix notation m ij equals vector I 0, the unperturbed vector, the unperturbed eigenstate I, m, and the unperturbed eigenstate j. So if m is our Hamiltonian correction h1, we get h1 ij, and this would be a very useful notation. Now we want to find the first order correction to the eigenstate n. To do this, we do similarly as we have done for the first order correction in the energy. We had multiplied the first order equation by the bra n0. Now we do the same, but not with the bra n0, but with the bra k0, where k is different. So k0 is different from n0. So if k is equal to n, we obtain the correction to the energy. If k is different from n, we will obtain the correction to the eigenstate. Let's see how. We write k0 here, and then we write it as like this. We are distributing the k0, k0, the n0 plus now this term here k0 h1 n0 minus k0 en1 n0 equals 0. Now this term here we see that k0 h0 it is the unperturbed eigenvalue equation, so this gives ek0 times the bra k0. Here we can take out en0 and we obtain this, and then here we can't do nothing, and here we can take out en1 and we get this. But remember that k0 and n0 are orthogonal, and so this cancels out and we are left with these three terms, and we can put together these two terms, so we get k0 n1 times ak0 minus an0 equals minus k0 h1 n0. Now we divide both sides. I write everything better here. We divide by ak0 minus en0 by ek0 minus en0, and here we have k0 minus k0 h1 n0. So we arrive here, and since we have no degeneracy, this will be different from 0 because k and n are different, so the eigenvalues must be different since we have no degeneracy. And here we can see that with this notation we can write this in a more compact form as h k n. So we have found this bracket product. How to find to isolate n prime? We use the completeness property. So we can write n1 as the summation of ket k bra k times n1, because this is the identity matrix by the completeness property, k0. And since when k is equal to n, this will be 0, we can sum for k different from n, so we can use this expression and put it here, and we get minus hkn divided by a0k minus an0. So we got our first order correction to the eigenstate n. Sorry, I forgot to put the 1 here. Now that we have n1, we can find the second order correction to the energy. Remember the formula for the k order correction to the energy, we need the k minus 1 correction to the eigenstate. So if k equals 2, we can expand this term, and we get n0. I write everything inside the summation, so we get minus the summation for k different from n0 h1 k0 times h prime kn divided by a k0 minus an. Now you see that this is, with this notation, h and k. So now I write it like h and k, sorry, h1 and k. So here we have h1 and k times h1 kn. I have just cancelled the definition, but actually we needed to show that h and k, h1 and k, which is n0 h1 k0, it is the complex conjugate of this inverting everything. So now the ket k0 becomes a bra k0, h1 is Hermitian, so h dagger is equal to h, and here we have the ket n0. So it is the complex conjugate of this, so the complex conjugate of kn. So when you invert rows and columns, you get the complex conjugate. So here we can invert the row and columns and take the complex conjugate. So we have h1 kn star, and so we have h1 kn star times h1 kn, which is the modulus of h1 kn squared. So we got this expression for the second order correction in the energy. So to sum up, the important relations we got, which are useful in many applications, they are the first order correction to the energy, the first order correction to the eigenstate, and the second order correction to the energy. So we can write the energy an as an0 plus this first order perturbation term multiplied by lambda plus minus this second order perturbation term multiplied by lambda squared k different from n of h1 kn squared ek0 minus en0 plus some terms big O of lambda cube, and then we have the eigenstate n, which can be written as the unperturbed eigenstate minus lambda plus lambda times the first order correction, so minus lambda the summation k different on all the k different from n of h1 kn divided by a0k minus a0n times the ket k0 plus big O of lambda squared. So these are the approximate solutions we have found. We got all the terms up to the first order for the eigenstates and up to the second order for the energy, and these have already many applications. So it's all for today. See you next time. It has been a pleasure.